Okay, so let's start with a discussion on the problems in assignment 1, and if you have time after that, we will do some, I'll give you some lecture on quantum mechanics. Okay?
Okay, sir.
So problem 1, which is basically about finding the eigenvalues of two matrices and whether or not these two matrices are that you can find simultaneous eigenkets. Do you guys have any questions about this question?
No, sir.
No, sir.
Nahi?
No, sir.
Okay, good. Problem 2, which is basically about deriving the continuity equation from Schrodinger's equation. How about that one?
This one I may be able to figure out, but I haven't really looked at it.
Yeah,
Okay.
same.
All right, so do you want me to discuss it in general terms, or?
I think
that
this
yeah,
would be a good idea.
yeah, that's great.
Okay, so problem 2, you have to derive something known as the equation of continuity from Schrodinger equation. So what is the equation of continuity? The equation of continuity states that you have some kind of a density of some fluid, and the rate of change of the density of that fluid with respect to time is balanced by the flux of the flow of the current density out of that region, which is represented the divergence of S, where S is the current density. Okay, so this is the equation of continuity, and is valid for any incompressible fluid. And the assumptions are that there are no sources or sinks of the fluid, okay? So the fluid, it cannot be made or destroyed. So examples are, for example, you can think of water. You know, water is a pretty good, given pressure and temperature, our constant water is a pretty good example of an incompressible fluid. And then you can have, say, number of particles which are, say, conserved. That also satisfies this. Charge is another thing. And in the case of Schrodinger equation, it's probability. Okay, the rho is representing the probability density, which in the case of quantum mechanics, it's given by this guy. And of course, because it's psi star psi, this is a positive definite quantity, right? And so you have to derive from Schrodinger's equation an equation which has this form with the probability density given by this expression, and the current density, which is a three-dimensional, three-vector, given by h by m, which is a real number, the imaginary part of psi star gradient of psi, which is also a real number. So this is a real number, right? And you are to assume, in general, that for the Schrodinger equation, that v of x is real. And in general, non-zero, okay? So don't assume that v of x is 0, okay? So from there, you have to, once you have derived that equation, you can integrate that equation over all space. So integrate the equation of continuity over all space to derive that q, which is the integral over all space of the probability density, which we can also write as like this, that this thing is constant, is a constant of time, that is dq dt, which is a total derivative, total time derivative. This is 0, okay? And what is this saying? This is saying that the normalization of the wave function is something that does not change with time in the presence and in the absence of sources and sinks. If, of course, there is a source which creates these particles, then, of course, this is not going to be true, but that's not what we are talking about here. Okay? So, hint, you may have to use to show this, you may have to use from the, there is a way to show this without using the equation of continuity, but I want you to show it using the equation of continuity. Well, there's a way of showing it without the equation of continuity, but you are implicitly using the equation of continuity. So one thing you may need is to use the two facts that, these are square integrable functions, which you have seen in your tutorial, right? So square integrable functions means that a function, psi, its modulus will go to 0 as its argument, the space-time argument, goes to infinity, right? So that's what it means to be square integrable in a sufficiently, a rapid manner, such that, this object is a finite number. That's what it means. So you are to assume that they are square integrable, and number two, you may have to use not Stokes' theorem, but Gauss's divergence theorem. Okay, so Gauss's divergence theorem. Okay, so what does Gauss's divergence theorem tell us? It tells us that if you have a volume integral, say d cubed x over some volume, and the integrand is the divergence of some vector, then that is equal to the surface integral. So it's dA. So this is a two-dimensional surface, and the integral is over some sigma, which is the boundary of that volume, of dotted with that vector. Okay, so this is Gauss's divergence theorem. So you may have to use it where the volume, in this case, will be all of space-time. All of space, sorry, not space-time. Okay. So these are the hints. That should be enough. Okay? Any questions or?
No, sir. I think I can solve it now.
Okay, all right. All right, let's move on to problem number 3. So problem number 3 is asking you to show that the wave function that minimizes the Heisenberg uncertainty principle, recall that the Heisenberg uncertainty principle says that the product of the uncertainty and the position of a particle and the uncertainty of the momentum of the particle is greater or equal to h bar by 2, right? So there must be some psi for which, this product is minimized. That is, this is equal to h by 2, right? And for other wave functions, it's going to be greater than h by 2. So you have to show that the psi that minimizes this, the wave function psi of x, which of course is x dotted with psi, this is some kind of a complex Gaussian, okay? And to do this, you have to revisit the proof of the generalized uncertainty principle. And, there you have to show that, for the generalized uncertainty principle, for that inequality to be saturated. So an inequality is saturated when you basically go and it goes to one of the limits. That is when the equal sign is satisfied. That inequality is saturated, for general A and B. Delta A squared times delta B squared is greater or equal to, the expectation value of A prime, B prime, where A prime and B prime are, basically the A and B operators, which are Hermitian operated, minus their average value, okay? So, that this is going to be equal when, of course, the right-hand side is minimum, okay? And so it's going to be, so essentially, you have to think about where did this relationship come from? And you have to remember that the relationship came from Schwarz inequality. Okay. And according to Schwarz's inequality, this is saturated, when it tells you, yeah, it's saturated. Hang on. Yeah, okay. So I'd like you to revisit Schwarz's inequality and show that, this is saturated when the anti-commutator is 0, and the commutator doesn't have to be 0. A weaker condition is this is true for some value of C. And once you show that, what you can do is that you can actually turn these equations for the operator A being X and the operator B being P. You can turn these equations into differential equations, okay? And these are essentially meaning that you can go to the position basis where X becomes replaced by the number X, and the operator P becomes replaced by minus I H bar d of dx, and psi becomes replaced by psi of x. And then you solve those equations to find that psi of x is a Gaussian, okay? So that's going to be the hint. So this might be a little bit more challenging than the other ones we have encountered so far. But I guess, Nahi, you have done it, right?
Yes, I haven't write it up, but yeah.
Yeah, but essentially you have. So did I make a mistake somewhere in the description or no?
No.
Okay. So any questions?
No, sir.
All right. Okay. Isa, did you have any question? You came a bit late. Did you have any question about number 1 and number 2? We have already covered those, but I can go back.
স্যার নাম্বার 1 আর নাম্বার 2 তে নেই তো তেমন কোনো সমস্যা নেই। এইটাতে নেই একটু মানে আপনি যদি আবার এটা একটু ডেসক্রাইব করতেন।
কোনটা নাম্বার 3?
নাম্বার 3 টা।
নাম্বার 3 কোন পার্টটা?
স্যার আমি প্রথম থেকেই মানে জাস্ট ধরতে পারিনি। স্টার্ট করেছেন।
Right. So let's look at the Schwartz inequality. Okay, what is Schwartz inequality? Schwartz inequality says that. Let me just bring up Schwartz inequality. All right. Can you wait 1 second? Let me get my other resource.
Yeah.
All right, right. So the idea is that when we derived, so when we derived the Heisenberg uncertainty principle, it's not here. So the generalized Heisenberg uncertainty principle is actually delta A squared, delta B squared greater than or equal to, I think there's a factor of 1/4, and there's a modulus, and then the expectation value of the commutator of A and B squared, right? I think that's it, yeah. So, but when we derived it, there was, this is not, because, in quantum mechanics, it's really the commutator that is important for us. That's where we went. But when we were deriving the Schwartz inequality, this inequality, what we did is that we derived a different, expression, which is delta A squared, delta B squared, and it's going to be greater than or equal to an expectation value of the product of A prime and B prime psi, okay? So that's basically what and from there we derived, what we did is that an A prime and B prime, these are defined by these equations. So A and B are Hermitian operators, and we are subtracting the average values from those operators, And therefore, A prime and B prime are also Hermitian operators with the, convenient value of their average being 0, right? So that's all that we are doing here. We are just shifting the origin. And then what we did is we basically, from this expression, we derived an expression where the right-hand side is a sum of the commutator, the expectation value of the commutator, and the expectation value of the anti-commutator, and there are, I think, factors of half and equal to 0. So this thing is equal to 0. Right? And then what we are going to say is that, when is this inequality, when does this inequality become becomes a equality, right? And so this equality so this equality, becomes an inequality, and so here we need to go and we need to revisit Schwarz inequality. Okay, so I'm just going to flip over to the place in my book where they discussed Schwarz inequality, so Schwarz inequality says that if we have, say, two this is it. So Schwarz's inequality is when is Schwarz's inequality satisfied? Do you know? Okay, so Schwarz's inequality is satisfied. So if I go back to say we have two kets, say V and W, and we take their inner product, then that is going to be less than or equal to the product of the length of these two vectors. So it's much more clear if I convert these to, say, a real vector, like three-dimensional vector. Suppose V was a three-dimensional vector and W was a three-dimensional vector. Then what would this equation become? This equation will then become that the left-hand side is the dot product of V and W, the absolute value, right? And this is going to be the length of V and the length of W. So, so if these are two vectors, their dot product, when is their dot, when is the dot product going to be the greatest? Because that's when, this equality will be saturated. If V is like this and W is like this, when will the dot product of these two things be greatest? Can somebody tell me?
When they lie along the same line.
Exactly, right. So when essentially when W is proportional to V. Okay, so you have to go and convince yourself that the saturation of the of the Schwarz identity that is given in problem 3 is equivalent to this. Okay, and once you have done this, you have been given two conditions, right? And now were you able to show that?
I still haven't write it out.
Yeah, no, I don't think that's something that was asked in the question. Okay, what was asked in the question is to show that if you assume condition 1 and 2, then the inequality is saturated. And is that something you showed?
Yes, sir.
Okay, so yeah, so show that, and then what you have to do is that those two conditions which are given here, take A to be X and B to be P, and use the fact that X in the position basis is just the number X, and P in the position basis is this differential operator, okay? And that the vector psi is just given by psi of X, okay? Then you can interpret these equations as differential equations. And these are first order differential equations, so it should not be very hard to integrate. And from there, you can find out what the Gaussian, that the function that satisfies this is going to be a Gaussian. Okay? Okay. Isa, is that fine?
Yes, sir.
Okay. Okay, let's move on to problem number 4. Do you guys have any questions on problem number 4?
This one seems easy enough. I haven't tried it, but it seems like I can do it.
Yeah, it's basically follows the tutorial 2, and it's just one more step than what you did in tutorial
Yeah.
2.
Pretty much the same thing.
Okay?
Mhm.
Okay, can we just hang on 1 second? Let me just. I'll be back. All right. So, anyone else has questions about problem 2? So let me just make it clear what I mean by problem 4. What I want you guys to do in problem 4. In problem 4, I first want you to show that Pxx prime, if I take the Hermitian conjugate, it's Pxx prime. And to do that, you have to use some delta function identities. And then you have to show that it's self-adjoint by taking psi, and Pxx prime and phi, and making sure that this thing, is also self-adjoint, right? So there you have to use the fact that psi and phi are functions which are, which are square integrable, okay? Okay, just give me 1 second because I think I need to rescue my cat from the dog. Hey, Ali. One word of advice is that in life you should not pick fights with something that is 20 times your size. Anyway, which my kitten seems to be ignoring. All right, so that's basically what we have to do, okay? And that's equal to, what is it? I forget, P, so I shouldn't really do this. that P is psi of star, right? Isn't that what it means to be Hermitian? Sorry, as a self-adjoint.
Yeah. Hmm.
Yeah.
Mhm.
কাজ করতেছি কাজ করতেছি একটু কাজ করতেছি মিটিং এ আছি আম্মা sorry my mom is here and she wants I have to tell her that I'm in a meeting so I'll be there okay sorry about that that's the problem of working from home kittens mothers and stuff like that interrupt all the time all right any questions
No.
okay anyone else
No, sir.
okay so problem 5 is probably one of the most interesting problems here and did you guys have any questions about that did someone do problem 5
Not yet, but I'm very lost just looking at it.
Same.
okay Nahi
I'm not sure. I didn't try it yet.
so okay
এটা কি বাই এনি চান্স আমাদের আমরা কি ইয়া থেকে আসবো মানে একটা সলিউশন ধরে জাস্ট আমি যদি এটাকে বলি যে আমরা ফুরিয়ার ট্রান্সফর্ম করে দেন হচ্ছে কি ফুরিয়ার ট্রান্সফর্মটাকে হচ্ছে কি আমি যেহেতু ফুরিয়ার ট্রান্সফর্মটাকে কে দিয়ে আমরা মানে কনভার্ট করে দিলে এভাবে এরকম ভাবে সামহাও আমি ট্রাই করেছিলাম একটু
Okay, let me just explain what I'm trying to do here. Okay, so the formal solution of the Schrodinger equation is the time evolution operator, right? So what it means is that if you have a state at some time, say t0, you can find out from that state the evolution of the state at a later time, say t, by applying the time evolution operator to the state at t0, right? Do you agree?
Yes, sir.
Yes, sir.
Okay, so this is basically what it means to do physics. In physics, I give you the initial condition of a system at some time. You find out by churning the machinery of physics what the condition of the state is going to be, what is the condition of the system is going to be at a later time, or a previous time, right? That's what it means to do physics. Physics is really about causality. Physics is about predicting what happens in the future. It's a very simplified, in a very simplified version of it. Not simplified, I would say, from a very grand scheme of things, philosophical point of view. That's what physics is. Okay? So now what I've also shown is that if I take say the state vector, which is something that Isa asked me as a question one day in class, is that if I take the same vector and project it onto the eigenbasis of the position operator, then we get something which is the wave function, right? This is the definition of the wave function. It's a projection of the wave of the state vector onto the position basis, position eigenbasis. So there should be an analog of this statement in terms of this thing, right?
Yes, sir.
Do you agree? Yeah. So what is that statement? Okay, so that statement is, so there is a version of this. So let's see. So let's start with this statement. And, because, we want things to be in terms of wave functions, let's multiply. So I'll be in one dimension to make life simpler, the notation simpler. Also, so I have to multiply this equation by x from the left side, right? Do you get what I'm doing?
Yes, sir.
Okay. And what is this? This is nothing but psi of xt. Right? The left-hand side. But what is the right-hand side? Well, to do the right-hand side, I'm going to do something. I'm going to use the fact that I have here an identity operator, right? The identity operator is everywhere. It's like God. So what we can do is that we can decompose the identity operator in terms of in the position basis. So I am going to insert the ket and bra and psi of t0, okay? I'm using the fact that the identity operator is equal to dx prime, x prime, x prime, right? Okay? I'm using this fact. Is that clear what I'm doing?
Yes, sir.
Okay. So, and then what is this then?
Psi h prime t.
Right, it's the wave function. So, and let's, what is this object? This is some function, right? Some number. Because if I sandwich an operator by two states, that thing becomes a number, right? Because an operator acting on a ket gives me a ket, but when I take the inner product with a bra, it becomes a number, right?
So this is what we're calling propagator, is it?
Exactly. So let's call that k. It's a function of x and t, as well as a function of x prime and t0, or t prime, or whatever you want to call it, times x psi of x prime t0, right? So what we are saying is that the wave function at the point x at time t, so let's draw the time axis in this direction, and space goes in this direction, okay? And there is some point in space-time. This is x and t. We want to find out what the wave function is at this point. Then what this equation is saying is that we need to know the wave function at an earlier time, say t0, and over all of space, okay? We need to know it at the earlier time at all of space. And then, we need to know this function. And what does this function do? This function is just telling us how to weigh this part of the wave function and how it propagates forward over here, okay? So, if this seems unfamiliar, it's actually not. Have you guys ever been, when you studied optics, were you ever taught Huygens principle?
I'm actually doing the course right now, so no, not yet.
Okay. Did anyone else know about Huygens principle?
I haven't done optics yet.
Okay.
So it's basically to express a composite beam in terms of point sources.
Right. So Huygens principle is a classical principle that Huygens, proposed because he wanted to explain how waves propagate, and there was not a good, understanding of waves at that point. And he said that, okay, suppose we have a wave front. He said that every point on the wave front can be thought of as a point source for another spherical wavefront, okay? So spherical wavefront, but in such a way that its intensity just, goes to zero as you go behind it in the backward direction. No. And then if you've done this for all the points, then you take the envelope of these new wavelets. And that's how you get the new position of the wavefront, okay? So in a sense, what we're doing is that we're saying that, well, quantum mechanics is a kind of wave mechanics, that we have the wave function at a given time over all of space. And then what we do is that, this guy, of course, depends on the Hamiltonian. So this, the specification of this function tells us how, given such a wave function, things can propagate forward in time. Okay, so this is a statement about causality as much as this is a statement about causality. Okay? So this is known as the propagator. A propagator has a very simple interpretation. And suppose that instead of a wave function that is spread over all space, you had a delta function. You had a delta function wave function over here. Okay, then this wave function would be zero everywhere except at this point, say, let's call this, say, x prime. Right? So then, what would your, this would be given by delta, say, x minus x prime, say, let's call it, say, x double prime. X minus x double prime, right? So then, what are you going to do? You're going to basically, you can do this integral very easily then. And your integral is going to be, well, what will be the result? K x t x double dot t0, right? Right?
Yes, sir.
Yeah, I've just done this integral using the delta function. So that is telling us that the propagator is equal to the wave function when the source in the past was a delta function. Okay, so you can think of the propagator as the propagation of a unit of a unit of your state vector. Okay, the delta function is kind of a unit when it comes to continuum, when it comes to functions, right? Or you can just say that, well, the propagator is essentially what you get if you evolve a delta function in time. Okay, so these are like different perspectives on propagators. They have relationship to differential equation, on the idea of causality, initial condition, Cauchy initial value problem, stuff that is going to come up in physics again and again and again. Okay, so that was the general introduction. And then what you're supposed to do in this problem is to show that for a particular kind of, so in general, it's very hard to find the exact expression for the propagator, because you have to realize when you find the propagator, you've essentially solved the problem. Okay, so it's only for very few, very limited number of Hamiltonians that you can actually exactly find this propagator. And one of them, of course, is the free particle, when the Hamiltonian is just p squared by 2m. Okay, another one would be the simple harmonic oscillator, which hopefully we will do sometime. Okay, so Now you know what u is. What is the expression of u in terms of h? I asked this before and I didn't get any answer. Today I'm hoping I will get the answer.
E over minus IHT
E over?
minus IHT.
Sorry, you have to tell me everything from the beginning.
So e to the power minus I over h car.
Oh, it's supposed to be power. I said over for some reason. It's
H bar, tapore?
T.
HT, right?
Yeah,
Yeah.
HT.
Right. So, right. And okay. So now you know what this is, the time evolution operator is. And then first you have to show that, you know, if you take a wave function, which is a wave packet, and it's a sum over, it's a sum over free wave. So you have an integral over dpa of p e to the power minus I h bar px minus p squared by 2m of t, that this is a solution to the free Schrodinger equation. Do you think you can do that?
I'm not sure. I'll have to try it myself first.
Yeah, okay, try it yourself first. Okay? All right, so I'll let you guys do that. So you just have to plug it into Schrodinger equation without a potential to see if the left-hand side and the right-hand side agree. Okay, do you think it's going to be very difficult? You just have to know how to do differentiation, right?
Yeah, it doesn't seem too difficult.
Yeah, okay, so I'll let you guys do it. Isa, what do you think? Do you think it'll be hard? So
Not that much.
Okay, what is the Schrodinger equation, free Schrodinger equation? Can you tell me, Isa?
Sorry?
What is the free Schrodinger equation?
Just we have to minimize the potential part.
No, it's IH bar d psi by dt is equal to minus h squared by 2m b squared dx squared of psi, right?
Yes, sir.
We don't have a potential.
Yes, sir. Okay, sir. The potential just
Yeah, 0 করে দিচ্ছ. So now you have to take this expression of psi. It's a function of x and it's a function of t. And the function of t is explicit, the function of x is explicit. You don't have to do anything with these guys because they are just functions of p. So they are not going to depend on t or x. And you just have to take the derivative with respect to t and the derivative with respect to x twice and see if they match. Okay, so this is easy. You should be able to do this. You know, read the questions carefully because the question is just going to guide you to the answer. Okay, and the second one is it's basically you have to apply the fact that if you have if you know this is a Fourier transform of something, right? It's a Fourier transform. It's a Fourier integral. It's a Fourier transform of AP. So, you know, AP, whenever we have a function, f of x, and we express it as a Fourier transform, well, I'm just not going to use a h bar here, but, you know, in general, the Fourier transform is with respect to something called k, and there's a square root. That's my convention. And you have a of k e to the power minus I kx. So here I'm going to encourage you to go back and look at the notes from Quantum 1 Plus. Okay. And then A of k is then 1 over square root of 2 pi d of x f tilde, sorry, not f tilde, f of x e to the power plus I kx. Okay. So now what I can do is that I can take this expression and evaluate and replace this by this expression. Then what do I get? I get f of x. So I get 2 factors of these. So this becomes 2 pi. There's no h here because I'm not doing quantum mechanics per se. And then I have d of k, but then I have d of x. And then what do I get? I get, but we don't get d, we don't get d of x because this is a dummy variable. So I have to use x prime here, right? Because, I'm integrating over x something, and here I have x, so it has to be x prime. And therefore, we have f of x prime, and we're going to get from here I e to the power plus I k x prime, and we had before that minus I k of x. And that's exactly what I want you to derive. You just use it twice. But of course, in the quantum mechanics, there's an extra time variable, and you just have to think about that. And of course, when you compare that with this equation, you get an expression for k, obviously an integral expression for k. It just kind of pops out, right? So write down that integral expression of k, and it'll be an expression for k that involves an integral over the momentum. And because it's a free particle, those momentum integrals will just be Gaussian integrals. It may have a complex Gaussian, but it's a Gaussian integral nonetheless. And you should be able to do that. When you do that, you find the expression, the explicit expression for the propagator for the free particle. By the way, those of you who are doing mathematical physics, there's also a way of deriving this propagator using the path integral, which Shubho may or may not have shown you. It's something that I will show you further down the line in this course when we cover path integrals, which I'm hoping to do.